And up next, it is my pleasure to introduce Sandy Yuan. Sandy is a postdoctoral fellow here at KIPAC, and he is going to be telling us all about how we can learn about real physics using fake universes.
Hello. All right. Yeah, so I'm a postdoc here at KIPAC, and let's get into it. So there are, a lot of very important questions in cosmology, such as what is the composition of the universe, how much dark matter, dark energy there is. And there are also important questions surrounding how structures form. So a lot of this information, the answers to these questions, are embedded in the late-time 3D distribution of matter in the universe. So if we can measure this distribution of matter, we could potentially, get some handle on these important questions. However, it's not super straightforward to actually observe the distribution of matter in the universe, as most of it is dark matter. So that's why we try to go after, this using various visible tracers. So we learned this yesterday from Elizabeth that, you can go after the positions of galaxies. You can look at how, mass affects the path of light. You can look at absorption of light coming from some distant background. But probably the most mature way of going after the distribution of mass in the universe is through the positions of galaxies. So that's why we built, these very expensive experiments such as DESI, such as Rubin, to try to map out the positions and properties of millions and billions of galaxies in the universe. However, being able to observe a lot of galaxies is really nice, but that's not, the full story. Being also able to model the positions of tons of galaxies is equally important. And, the kind of standard approach is to write down the relevant physical equations on the blackboard and try to solve them and try to predict some relevant aspect of the data, and then use that to try to infer what the underlying parameters of your model is. However, that can only let you get to only part of the information in the data. There are, especially, as you try to, in cosmology, we say we go to nonlinear scales, where the physics becomes a lot more complicated, where the gravity starts to get mingled with the physics of galaxies, baryon, stars, and the equation solving becomes a lot more difficult, at least from the perspective of a postdoc standing in front of a blackboard. It becomes very hard. So that's why we use computers, especially supercomputers that can crunch through billions and trillions of calculations in the matter of seconds. So that by using these supercomputers to run these simulations, we can get to smaller scales and hopefully learn, build models for galaxies and cosmology at the same time, and learn a lot more physics from the 3D distribution of matter in the universe. However, it's not. Okay, so this is a picture of a suite of simulations we ran. It's called Abacus Summit. It's huge. It's got 60 trillion particles. So that's more than all previous cosmological simulations of dark matter combined in terms of how many particles there are. So my research really focuses on trying to model the 3D distribution of galaxies in the universe using these simulations. There are a lot of complexities in these models. Specifically, these simulations only give you the distribution of matter. So you have to paint on galaxies and try to figure out what's the correct and robust, accurate way to model galaxies in these simulations are. And another aspect of work that I spend a lot of time on is think about how do you actually summarize the information effectively from the observed distribution of galaxies. So Tom and I are big fans of these kth nearest neighbor statistics that we found to be very informative, a lot more constraining than two-point correlation functions, yet still being lightweight and easy to handle. So I'm just going to show this one plot where we have applied a kind of this simulation-based modeling pipeline with the kth nearest neighbor statistics to a blind mock challenge that's led by Elizabeth. And basically, we found that our pipeline can constrain cosmology very well, and we have devised a set of statistical techniques to demonstrate that our methods are robust. But there are still a lot of challenges lying ahead. Need to figure out a ton of observational systematics associated with using new statistical tools, and also need to stress test our models more to make sure we are ready to apply the data. Thank you.
Hey, thank you, Sandy. Any questions? Yes.
Hi, could you just explain the graph that we're looking at right now? I'm a little confused.
Yeah, sorry. So these are two cosmological parameters. You have the this is the amount of dark matter there is in the universe, and this is the amplitude or the height of the density peaks in the universe. And this is what's called a contour constraint. So what these circles mean is like, what's the preferred region of this parameter space that our data that we can infer from the data. So the different tiers is like this. The inner circle is 68% times we think the true value falls in that contour, and the outer circle is 95% of the times we think the value falls in that contour. So it's kind of a confidence plot. Mm-hmm.
Any other questions for Sandy before we move on? Well, if not, let's thank Sandy again.